Hello and welcome to our third lesson, which is calculating limits using limit laws part 2. So last lesson we looked at if you were finding the limit of a polynomial or a radical, and today, or rational, sorry. Today we're going to be adding radicals in. So we reviewed how to rationalize denominators. We also talked about the fact that we would sometimes see questions where you were rationalizing a numerator instead. And this is where we're going to be using that today. So just a reminder, when you are rationalizing, the goal was to try and get rid of a radical on the denominator if you were rationalizing a denominator so that you no longer had one there. Sometimes we're going to be trying to be getting rid of the radical on a numerator instead. And we do that by multiplying by the conjugate. So for example, if we had 1 over 4 plus root 3, we would multiply by 4 minus root 3, and we called this the conjugate of 4 plus root 3. So if I take a look at this limit, if I try direct substitution, what's going to happen is if I do f of 0, I get 1 minus root 1 minus 0 over 0. Automatically, we see we're going to have an issue because you've got a denominator of 0. Now, if I keep going, I get 1 minus root 1 over 0, which gives me 0 over 0. Now, from our rules last day, this tells me I should have a common factor, but I don't because we've got these radicals. So our new technique today will be to rationalize so that we no longer have this radical on the top where we end up with 0. And we will be fixing this up a bit so that we can actually plug our x value in and figure out our limit. So the first thing, I'm just going to rewrite this whole question so I have a bit more space. So I've got the limit as x approaches 0 of 1 minus root 1 minus x over x. So I want to try and fix this up. So I'm going to multiply by the conjugate. I don't have a radical on the bottom. Therefore, my conjugate is of the numerator. My conjugate would be 1 plus root 1 minus x. I can't just multiply the top. I need to multiply the top and the bottom when I am rationalizing. Once I do that, on the top, I still have limit. I haven't plugged in my x value yet. I need to keep writing limit. On the top, basically, this is an expanding a difference of squares. I would get 1 minus x. On the bottom, I'm going to leave it factored. I do not want to expand those brackets. If you do, you're just going to have to simplify it again later and factor it back out. So hopefully these sorts of things will start to ring some bells from our review chapter that we did, and this is why we reviewed these skills. Okay. Now on the top, I've got limit as x approaches 0 of 1 minus 1 plus x if I expand these brackets here. On the bottom, again, leave the bottom factored. I only ever expand where I was multiplying by that thing's conjugate. So I multiplied by the numerator's conjugate, therefore I will expand my numerator. I will leave my denominator. Okay. Now the ones on the top are going to cancel out, 1 minus 1. This is going to give me the limit as x approaches 0 of x over x times 1 plus root 1 minus x. Now we see that the x on the top and the bottom cancel out. So just be careful here. A lot of people forget that that conjugate that we have left is on the bottom. So this gives me the limit as x approaches 0 of 1 over 1 plus root 1 minus x. And now I can substitute. When I direct substitute in here, I'm going to get 1 over 1 plus root 1 minus 0, or 1 over 1 plus root 1, or 1 over 2. So as soon as you see a radical, if you direct substitute and you get 0 over 0, you need to multiply by the conjugate. Then you can try direct substituting again. So again, for example, if I try this one here, I do f of 0, I get 0 over 0 on the top right now. We're okay, that's fine. Okay, then on the bottom, I get root 3 plus 0 minus root 3, which gives me 0 over root 3 minus root 3, which gives me 0 over 0. And when you're doing these questions, most of you will just plug it into a calculator and see that it doesn't work, or you'll do it in your head. This side bit here and this side bit here, you probably won't actually write down. Okay. This tells me I need to multiply by a conjugate. Now the problem is here, my conjugate's on the bottom, so I need to multiply by the conjugate of the bottom. Conjugate of the bottom, you're changing that middle sign. So you would have root 3 plus x plus root 3. We also need to multiply the top by the conjugate. You must multiply by something equal to 1. You can't just multiply the top or the bottom. You must multiply the top and the bottom. Okay. This now gives me the limit as x approaches 0 on the top. That's not the conjugate of the top, so I'm going to leave it factored. On the bottom, this again is a difference of squares that's being expanded. The first term squared is 3 plus x, minus the second term squared is 3. This means on the bottom, I have a 3 minus 3. Those cancel out. This gives me the limit as x approaches 0. X on the top multiplied by the conjugate. Again, don't expand it. On the bottom, we get x. Now we've got an x on the top and the bottom. These can simplify because on the top, it's a factor. Now I'm left with the limit as x approaches 0 of root 3 plus x plus root 3. It was on the numerator, so it stays there. There is no denominator anymore. Now I can direct substitute. I get root 3 plus 0 plus root 3, which gives me root 3 plus root 3, or 2 root 3. The next part of today is what if we are looking at absolute value functions? Again, we reviewed these. We reviewed the fact that if you have the absolute value of x, it will equal itself if x was already greater than 0. So for example, the absolute value of 5 is just equal to 5. But if x is less than 0, it equals to negative of itself. So the absolute value of negative 5 is equal to negative 5, which is equal to positive 5. We also remember, hopefully from math 11, as well as our review, that if you have something like the absolute value of x minus 4, this can be split into itself if x is greater than or equal to 4, and the negative version of itself, x is less than 4. So if I remember what this looks like as a graph, x minus 4 looks something like this, right? And so this here would be the x minus 4 portion, and this here is the negative x minus 4 portion. And this value here where it switches direction is at an x value of 4. Okay, we reviewed this in our review chapter. Okay. So now if I want to find each limit of an absolute value, again, we can't direct plug in unless it's in our domain. Our domain here is x can't equal 3. I'm approaching a non-permissible value. So that tells me we know at non-permissible values, we either have wholes or asymptotes. So I'm either going to need to be finding a common factor or a left-hand and right-hand limit. I can't find a common factor here because I have an absolute value on the top. So I need to write two cases. What I have here is I'm approaching the point in our V, basically, where I switch direction of my absolute value. So I need to break this down into a positive case approaching from the right and a negative case approaching from the left. Okay. So I'm going to rewrite this as the limit as x approaches 3 from the right, absolute value over x minus 3, and the limit as x approaches 3 from the left, absolute value over x minus 3. So from the right, I would be approaching, again, if I think about this graphically, the absolute value of x minus 3 looks like this, right? This value here is 3, right? So if I'm approaching from the right, I'm on the x minus 3 portion, I approach from the left, I'm on the negative case, the negative x minus 3 portion. So if I approach from the right, I can rewrite this as the limit as x approaches 3 from the right of x minus 3 over x minus 3, because the absolute value equals itself if our x value is positive, right? So if I'm bigger than 3. On the other portion, I'm on this left-hand bit of my graph here. So this means I would have the limit as x approaches 3 from the left. I'm approaching that left-hand half of the v. So our absolute value is equal to the negative portion of x minus 3. Now on the bottom, we still have x minus 3. Now we have common factors that can be simplified. So the top one, we have x minus 3 and x minus 3 that simplify. So what I'm really doing is the limit as x approaches 3 from the right of 1. You know, the little limit of a constant is just itself. And on our other one, same thing, we have a common factor there that we can cancel out, which gives us the limit as x approaches 3 from the left of negative 1. And again, we know that the limit of a constant is itself. Therefore, our limit as x approaches 3 of the absolute value of x minus 3 over x minus 3 does not exist. So one more where we don't have the denominator, again, case 1 would be limit as x approaches 3 from the right of the absolute value, which we just saw if you're approaching from the right, this would be equal to x minus 3, which is just 3 minus 3 or 0. If I was approaching from the left, I would have the limit as x approaches 3 from the left of negative x minus 3, which would give me negative 3 minus 3 or negative 0, which is still 0. So therefore, the limit as x approaches 3 of the absolute value with no denominator would just be 0. And again, if you think about this graphically, this is what the absolute value of x minus 3 looks like. There's my 3. If I approach from the right, my y value approaches 0. If I approach from the left, my y value approaches 0. The last one for today is a piecewise function. So piecewise functions, again, we reviewed how to graph these, what they look like. And we know there's a couple different ways we can see piecewise functions. We might have things like, and I wouldn't write this down, this is just kind of scribbles here. We might have things like you have a function coming around and ends here on one piece, and then your next function starts in the same spot and proceeds something like this. You might have something where your second portion starts down lower like this and goes up, right? You might have something where you just have a hole and this continues, but you have one redefined point somewhere. So if you think about this in terms of limits, what you're really trying to figure out is as you approach this value from the left and the right, what is my y value approaching? Are my pieces connected or are my pieces not connected? Those sorts of things. So what we need to figure out is when we are approaching a value with a piecewise function, are we approaching a value that is distinctly on one of the pieces, or are we approaching the value where we are switching pieces? So for example, this one we're looking for the limit as x approaches 2. And I can see here that 2 is where I'm switching from one piece to another. So I need to consider my left and right hand limit. If the limit here said the limit as x approaches 10, we wouldn't need that. We are very clearly, if x is 10, we're very clearly on this piece. 10 is vastly bigger than 2 when we're thinking about a limit, okay? We could just direct substitute into that piece alone and find the corresponding y value. However, because we are approaching this border point where we switch pieces, we're switching between the one piece and the other piece. You need to consider as we approach the right and the left, what is happening. You can graph it if you want, but sometimes these can get quite messy. Okay? So if I look at the limit as x approaches 2 from the right of f of x, this is the limit as x approaches 2 from the right of this piece here, 3x minus 2, because this is where you have slightly larger values than 2. Okay. If I want the limit as x approaches 2 from the left of f of x, this is slightly smaller values than 2, which would be this piece here, x squared. Now, in both of these, 2 can be directly substituted in. We don't need to do any sort of simplification or anything here. So this top one would be 3 times 2 minus 2, which gives me 4. This bottom one would be 2 squared, which also gives me 4. And therefore, our limit as x approaches 2 of f of x is equal to 4. So some of you might say, well, why can't I just plug it into the bottom piece? Because the bottom piece is where you have or equals to. The problem is because if you think about this graphically, okay, what this looks like graphically is when x is less than 2, we have this parabola like this. Okay. When x is greater than 2, we have this line that goes like this, right? So the problem that we have is, what if this was not here, but down here? What if this was x squared minus 4? Okay. If we only consider the bottom piece, the piece that has the or equals to, we would only be considering this piece right here. And we would say that our limit is 4. But actually, our limit does not exist. The y value you approach from the left and the right would be different. So you do need to consider both pieces, even though one of them says or equals to. You need to consider both pieces in a piecewise function limit if you are approaching that border point, that x point where you switch from one piece to another. You can graph it too if that helps you. So this next one here, same thing, we're approaching 4. 4 is the point where we switch pieces. So I'm going to have the limit as x approaches 4 from the right, f of x, which for us means we're slightly larger than 4. Slightly larger than 4 is that bottom piece, 2x plus 1. I can direct substitute into that, and I get 2 times 4 plus 1, which gives me 9. Now, if I consider the other piece, even though we're not on this piece at exactly 4, we're still approaching 4. We'd be on the top piece, would be x plus 1, which gives us 4 plus 1, which gives us 5. These limits are not equal. Therefore, the limit as x approaches 4 of f of x does not exist. And again, if we think about this graphically, this should make some sense. Okay, we've got an x value of 4 here. If we're bigger than 4, we're equal to 2x plus 1. If we're smaller than 4, we're equal to x plus 1. Okay? Those pieces don't connect. Approaching from the right and the left give us different values. Okay? So yes, f of 4 is equal to 9, but the limit as x approaches 4 of f of x does not equal 9. So this is where that distinction between being exactly at that x value and approaching that x value make a difference. So a couple things from today, very specific situations. One is if you are dealing with a radical inside of a limit, if you can direct substitute, great. But if you have a non-permissible value that you are approaching, you will need to rationalize. 2, absolute value functions. If you are approaching that border point where you switch the different sides of the V shape of your absolute value, you need to break that into 2 cases, left-hand case, right-hand case. And lastly, piecewise functions. If you are approaching the point where you change pieces, you need left-hand and right-hand limits.